And we're back at it again. All right, so welcome to me. Last couple of days, y'all been messing around with batteries a little bit, just to kind of introduce what we're doing. So let's go ahead and define some of the things that you've been looking at and exploring. We're going to go through voltage, current, and resistance. Again, hopefully you're taking notes. Usually going to get some bonus extra credit for doing so. So pause me as you need to, rewind when necessary, and hopefully if there's any questions going along with this, you can answer them. So we're going to try to answer the questions of what is voltage. We're going to look at what's current, what's resistance, and how does all this factor into what's called Ohm's law. And those are basically the vocabulary terms that we have to kind of go over. Okay, so voltage is the thing that, if you want to think of it, it causes the electricity to move. One of the things about the voltage that relates to things we've done before is it's about potential difference, and it's about potential energy. And so when we are measuring the voltage, usually we're measuring it between two different points. And so when we're talking about electricity being able to move, it's going to move because there is a potential difference. It's again similar to, why does something fall? It's at a height, and it's going to go to a smaller height. So it's going to be able to fall. If it's just moving along sideways and it doesn't change its height, then it's not really had any change in potential difference. It's not really doing any work. So voltage is going to cause the electricity to move. And when we measure it, we're kind of measuring the difference in the potential energy that it has. We can also think about this as how much energy is left between 2 points. There's a difference in the electrical energy between 2 points. And usually, we're talking along a wire, or in some case of a circuit that we have. Okay. Another way to think of it, when we talk about a battery, if a battery is a 9-volt battery versus a 1.5-volt battery, so if we have these guys right here, that's a 9-volt battery, that gives us an idea of how much work this is able to do, how much energy this thing has, how much change it is able to cause. So when we quantify that, for example, with this, it gives us an idea of how bright can it make a bulb. A 9-volt battery is going to have a lot more ability to make a bulb bright than a 3-volt battery or a 1.5-volt battery. Okay. Some other things to think of, voltage is kind of like a water pump. And with a lot of electricity, you can almost think of it like water because it moves. If we need it to move faster, we have to pump it harder. And effectively, the battery is our pump. The higher the voltage is on the battery, the stronger it's going to be able to pump something, the more it's going to be able to move through the wire, and the more energy it's going to be able to transfer. So again, a higher voltage is going to be able to push current more. Again, this is a 9-volt battery. Car's got a 12-volt battery. We plug things into the wall, it's 120 volts. You plug your dryer into the wall, it's 220 volts. Again, certain things need more energy to be able to work when they're doing electricity. And voltage is going to be the thing that is going to be able to push the electricity through various things. Some things don't need very much electricity pushed through, so it's going to be a low voltage. Adding batteries together would increase voltage. So if I take two 9-volts and put them together, and we get 18 volts. Now I need to connect them properly. I would need to connect a negative to a positive in order to basically add them together. As opposed to this diagram that we have down here, where you've got two batteries, but they're facing opposite ways. And so if I try to get electricity to run out of the left side of this left battery, there's no reason for it to go anywhere because the right side of the right battery is also 3 volts. There's no potential difference. And so 3 volts doesn't want to move to where 3 volts is because they're already balanced out. So this is another example in science of where things are kind of want to move to try to balance things out. 3 volts will move to 0 volts because that's fewer. So voltage always wants to move from a higher voltage to a lower voltage. Right. In this illustration, the current's actually not going to flow, even though we have two batteries. We've got them hooked up the wrong way. You may have done this when you've replaced batteries in remote control or something. If you don't put them in the correct way, the thing still doesn't work. All right, so moving on to current, we just said that voltage is what pushes the current. Current is the moving electron. If you've seen your FET illustration, you saw the little minuses moving through the wires. That is our current. If you got more current, then that means there's more electrons moving. And if we've got more electrons moving, then effectively we've got more energy able to do some things. So if there's more current, there's more speed with a motor, for example, there's more brightness with a bulb. That's kind of how we measure current. Again, think about water going through a hose. If you've got more current, there's stuff moving through it faster. Current is directly proportional to voltage. That means as one goes up, the other goes up. So in this illustration, comparing top to bottom, The only difference is the bottom one has a 6-volt battery, the top one has a 3-volt battery. And you'll notice the the bulb on the bottom is brighter than the one on the top. So more voltage results in more brightness because more voltage results in more current. So mathematically speaking, if you double the voltage, you double the current. Right? And the last part of this is the resistance. Resistance is what slows down the current. So in the illustration we have over here, this will be our light bulbs. That is the resistance, kind of like squeezing the water hose. It kind of keeps the current from going through. Different devices squeeze differently. Some devices squeeze very little because they don't need very much electricity. Some devices squeeze a lot. And for example, if something squeezes a lot, we might need a bigger voltage source in order for it to be able to actually work. So there's kind of a lot of variables as we kind of think about these three things with current, voltage, and resistance about how they operate together. Resistance is, again, the thing that we want working, but we need to make sure that it's got the proper current going through it and has the proper voltage on it. Resistance is inversely proportional to current. Again, that means up and down. So if I have a greater resistance, that is going to lower the current. And it's usually that the resistance is affecting the current and not that the current is affecting the resistance. Between these three things, the current is the one that it doesn't really necessarily affect either of the other two. All right, voltage can change the current, resistance can change the current. Current doesn't really change either of the other two, though. So it's kind of this illustration right here to kind of put the three together, because when we get to Ohm's law is that there's a relationship between the current, the voltage, and the resistance. This is kind of the way that it looks. So the movement of the current is basically dependent upon how much the volt is pushing it, divided by how much the resistance is squeezing it. And that tells us how much current we've got. So if volt pushes harder, we're going to get more current. If resistance squeezes harder, we're going to get less current, and that's going to be inverse. So if the V gets bigger on top of the fraction, the I is going to get bigger in the answer. If the R gets bigger in the fraction, then the I is going to get smaller. Right? So this can be rewritten in several different ways depending on how you need to use it. So just a few things to review, and we're going to wrap up. So if we do several of these things, what's going to happen? If I increase the voltage, what's going to happen to the current? So again, more voltage, that's more push, so we should be able to get more current. If I decrease the resistance, if I don't squeeze as hard, what's going to happen to our current? It's going to pick up. Again, think about squeezing a water hose or something like that. If I get more current, what does that do to the resistance? Or, and this is kind of, again, usually the current doesn't cause anything, but if the current got faster, what probably happened to the resistance? We got less of it. Less voltage, if we're not pushing as hard, what's going to happen to the current? It's going to go down. If the current does go down, what must have happened to the voltage? Again, the current's not going to change the voltage, but if the current does go down, the voltage must have also gone down. And again, if we've got more current, what's going to happen to the bulb? We should see the bulb as being brighter than it was initially. A couple math problems of how that we would go about doing this. So if you will have some math problems with this. Again, our formula is pretty straightforward with doing this one. So again, voltage is current over resistance. That's one way to be able to look at it. I think I'd actually just got that wrong. Let me go back and make sure that I know I just said that wrong. So I'm gonna go backwards with this because I just got that one backwards. It's actually V equals I times R. I was writing it in a different way. V equals I times R, not V equals I over R. So let me get that one straight. I'm doing something from memory right here. This is also when I do these with one take. I don't have time to go back and do all this again. So sometimes I make a mistake and I will catch it on here. So voltage is current. And again, you'll have this on your formula sheet. Current times resistance. I stands for current. Has to do with the French word. It's kind of weird, I know. So if I've got a 12-volt battery and a 3-ohm resistor, then 12 equals I times 3. We divide both sides by 3. So 12 over 3 equals our current. And so our current would be 4. And current is measured in amperes, which is usually shortened up as an amp. Okay. Find the current if we had a circuit with 4 volts and there's supposed to be an ohm right here, a symbol. A resistance has a Greek letter that we use to describe the ohms on there. So it looks kind of like a little bit of a horseshoe. So we use V for voltage. We use this ohms for the resistance, and we use I for current, which in the units are going to be amps. So there's a lot of words to kind of keep straight here. But the current in this case, again, voltage is current times resistance. The voltage is 6. I don't know the current. The resistance is 2. What times 2 is 6, or 6 divided by 2 equals I. So our current is 3. So the current is 3. And again, use the letter I for current, but we use the units amp there at the very end. Okay. And then finally, the last one, how much voltage gives 5 amps of current through a 3 ohm light? So again, start with our formula, V equals I times R. How much voltage? And I would just multiply these two together. Okay. So 5 amps, that's my current. 3 ohms is my resistance. We multiply those together, and that's going to give us 15 volts. So the math is pretty basic. You're going to have some problems to work here in a minute just to get some practice with. But again, these should be pretty easy for you to go through. So again, voltage is the push of the electricity. Current is the actual movement of the electrons. The resistance is what's going to be using that current to slow it down. And the relationship between all three of those ends up being Ohm's law, which is voltage has the relationship of the current times the resistance. And again, as voltage goes up, current goes up. As the resistance goes up, the current's going to go down.